Hi everyone. We're now going to start looking at some examples to get a better idea of how to analyze code in terms of efficiency with our big O in mind. Now the first thing we're going to look at is lists, and more specifically, the operations we do on lists and what the big O is. So if we look at this code, we have a list L, which is of size n, as we're going to call it. Here, of course, it's of size 6, but more generally, let's imagine that it's of size n. Now, the first thing we do is L.sort. Now, one thing to always remember is that when you do sorting, a built-in sort method, you always have to assume that the language implements the fastest possible sort. Now, if you remember from a few weeks ago, the fastest sort that we learned was n log n, which was basically merge sort. So Python implements a similar sort, which is also n log n. So whenever you use a built-in sort, the big O of that is going to be n log n, where n is the size of the list. Here we do L.sort, but we say reverse equals true, which means that we're still reversing the same number of elements, so it's still n log n. Here, interestingly, we index into the list, which is a constant time operation. What that means is that no matter the size of the list, it takes the same small amount of time to get into a specific index. Then we subtract 5 from it. We subtract 5, which is also constant. So overall, this is a constant time operation, O of 1. Here we print, so L.count of the first element. Now it turns out that to count the number of elements in a list, it takes O of n. And imagine if you needed to count the number of elements on a list, what would you do? You'd go element by element, looking at each one and seeing if it was what you were looking for. Since there's n elements, and we have to look at each one, it's O of n. Here we do sum, which once again, you have to add up all the elements, so it takes O of n. Now, because we're doing this and then this, it's an O of n operation, and then another O of n operation. So overall, it takes 2n operations, but that's big O of n. So these are some examples with sequences. Now let's look at nesting. Now, nesting is interesting because in the last example, when we had something like this, where we did the sum of L plus the sum of L, remember that it was big O of n plus big O of n. So overall, it was still O of n, because n plus n is basically still n, because we don't care about constants. However, when we do nesting, we have to start taking into account multiplication. Now, the way that I like to look at it is that you want to see the number of passes, which is usually in some sort of for loop, and then the amount of work done at each pass. So we have this list L again. We do for C in L. Now, for C in L means that this for loop, the number of passes, is going to be n times, because there's n elements in L. Then inside of here, we do L of 0 plus equals C. So once again, we do that constant time operation. However, then we do L.sort. Now remember from last time that .sort is n log n. However, the big O of this entire for loop is going to be the number of passes times the amount of work. So let me write that down. The number of passes times work in each pass. Now in this situation, the number of passes is n, and the work we do in each pass is constant plus n log n. So overall, it's n log n. Thus, this means that this function has an n squared log n big O. So this is interesting because it's different than the function families we've seen before, but it's because we do n log n work n times. We sort the list n times, and so the overall big O is n log n. Notice here it says that we print L, and it says that it's an O of n operation. And the reason being is because to print a list, we have to print each element individually, which means they would take O of n because there's n elements. Now we'll look at an example of function composition. Now this is also interesting because when we sort a list, we have to remember the number of elements we're sorting because that's what n represents. So here we have our list L, and we first call G of L. Now inside of G of L, what we do is we basically say L times the length of L. Now if I multiply a list by some number, it'll just create a new list which has that many elements. So like let's say that I had L, let me make this a little bigger. L is equal to the 1, 2, 3. If I do print L times 4, it would be 1, 2, 3 repeated 4 times. So we're multiplying a list of size n, multiplying it by n. So now this new list has the old list repeated n times. So it actually has n times n elements, which is n squared. So the key to note is that g of L returns a list that is size n squared. So now we call f on this list. Now when we call f all it does is sort the list. So because we sort it, we assume that it's n log n. However, this is false because let's remember the size of this list. L was passed in from G. G actually gave us a list of size n squared. So what this means is that we do in this case, our n is equal to, so we know that sorting is n log n. Now in this case, our n is equal to n squared because the size of the list is actually n times n. This means that it's actually not just n log n, but it's n squared log n squared. So this is actually more than n log n because the size of the list, in terms of the original n from the original list L, is actually n squared. So if we reduce this, this is actually equal to n squared log, and then from log rules, you can know that because we have a log n squared, we can move the 2 to the front. So it'd actually be 2n squared log n, which is just equal to n squared log n. So interestingly enough, we have a much different big O because of function composition. So always remember when you're calculating the big O in terms with using lists, to remember the size of the list in terms of n is really important. For instance, if we had an n squared size list and we tried to count the number of elements in it, it wouldn't just be O of n, it would be O of n squared because the number of elements in there is n squared. So these were some basic examples looking at sequences, nesting, and composition, and later on we'll look at some more in-depth examples.